The successful transmission of data depends principally on two factors: the quality of the signal being transmitted and the characteristics of the transmission medium. The objective of this lecture and the next is to be able to understand the terminology used in transmission and the concept of signals. Data transmission occurs between a transmitter and receiver over some transmission medium. Transmission media can be classified as guided or unguided. In both cases, communication is in the form of electromagnetic waves. Guided media is also referred to as wired or bounded transmission media. In guided media, the electromagnetic waves travel through a cabling system that has a fixed physical path. Examples of guided media are twisted pair, coaxial cable, and optical fiber. Unguided media, also called wireless, are methods that transmit electromagnetic waves without the use of physical means to define the path it takes. Examples of unguided media are air, vacuum, and seawater. A network is two or more devices connected through links. A link is a communications pathway that transfers data from one device to another. A direct link is used to refer to the transmission path between two devices in which signals propagate directly from transmitter to receiver with no intermediate devices other than amplifiers or repeaters used to increase signal strength. A point-to-point connection provides a dedicated link between two devices. The entire capacity of the link is reserved for transmission between those two devices. Most point-to-point connections use an actual length of wire or cable to connect the two ends, but other options such as microwave or satellite links are also possible. When you change television channels by infrared remote control, you are establishing a point-to-point connection between the remote control and the television's control system. A multi-point connection is one in which more than two devices share a single link. In a multi-point environment, the capacity of the channel is shared, either spatially or temporally. If several devices can use the link simultaneously, it is a spatially shared connection. If users must take turns, it is a time-shared connection. Communication between two devices can be simplex, half-duplex, or full duplex. In simplex mode, the communication is unidirectional, as on a one-way street. Only one of the two devices on a link can transmit, the other can only receive. Keyboards and traditional monitors are examples of simplex devices. The keyboard can only introduce input, the monitor can only accept output. The simplex mode can use the entire capacity of the channel to send data in one direction. In half-duplex mode, each station can both transmit and receive, but not at the same time. When one device is sending, the other can only receive, and vice versa. In a half-duplex transmission, the entire capacity of a channel is taken by whichever of the two devices is transmitting at the time. Walkie-talkies and CB or citizens band radios are both half-duplex systems. In full duplex, both stations can transmit and receive simultaneously. The full duplex mode is like a two-way street with traffic flowing in both directions at the same time. In full duplex mode, signals going in one direction share the capacity of the link with signals going in the other direction. One common example of full duplex communication is a telephone network. When two people are communicating by a telephone line, both can talk and listen at the same time. Electromagnetic signals can be used as a means to transmit data. The signal is a function of time, but it can also be expressed as a function of frequency, which means that the signal consists of components of different frequencies. Like the data they represent, signals can be either analog or digital, and periodic or aperiodic, as we will discuss in the next couple of slides. The top figure shows an analog signal. An analog signal has infinitely many levels of intensity over a period of time. It is continuous, and transmits data in the form of a wave. An example of an analog signal is the human voice. The bottom figure shows a digital signal. A digital signal, on the other hand, can have only a limited number of defined values. Although each value can be any number, it is often as simple as 1 and 0. It is discrete and transmits data in binary form. An example of a digital signal is transmission of data in a computer. A periodic signal completes the pattern within a measurable time frame called a period, and repeats that pattern over subsequent identical periods. The completion of one full pattern is called a cycle. We can have a periodic analog signal as shown in the top figure, and a periodic digital signal as shown in the bottom figure. Unlike a periodic signal, an aperiodic signal changes without exhibiting a pattern or cycle that repeats over time. Since the signal is a function of time and can also be expressed as a function of frequency, the relationship between time and frequency is f equals 1 divided by t, which is equivalent to t equals 1 divided by f. Thus, frequency is inversely proportional to time. The table shows the common units and their equivalents in seconds. For example, the prefix milli represents 10 to the negative third power, and micro represents 10 to the negative sixth power, and etc. Similarly, kilo represents 10 to the third, and mega represents 10 to the sixth, and etc. In this example, we will see how to apply the frequency formula from the previous slide. In this problem, we are trying to determine how many seconds it takes to display one picture for both the computer screen functioning on 60 Hz and an HD TV on 75 Hz. Since we know that t equals 1 divided by f, we just substitute the frequency into the formula and solve for t. Thus, for the computer screen, t is equal to 1 divided by 60, which is equal to 0.01667 seconds. For the HDTV, t is equal to 1 divided by 75, which is equal to 0.01333 seconds. The sine wave is a fundamental periodic signal. A general sine wave can be represented by three parameters: amplitude, frequency, and phase. Peak amplitude, represented by a capital A, is the maximum value or strength of the signal over time. It is usually measured in volts. The greater the amplitude of a wave, then the more energy it is carrying. Frequency, represented by a lowercase f, is the rate in cycles per second, or hertz, Hz, at which the signal repeats. Related to frequency is the period, represented by a capital T, of a signal, which is the amount of time it takes for one repetition. The period of a signal is t equals 1 divided by f. Phase, represented by the Greek letter phi, is the measure of relative position of a point in time or instant within a single period of a signal. In the figure, we see an example of two different signals with the same phase and frequency, but with different amplitudes. The signal in the top figure, figure A, shows a high amplitude of the same signal frequency and phase, and the second signal in the bottom figure, figure B, is with a lower amplitude. It is notable that the signal in figure A will travel longer than the signal in figure B. In this example, we see two signals with the same amplitude and phase, but with different frequencies. In the top figure, figure A, we can see that there are 12 periods in 1 second, which makes each period equal to 1/12 of a second. Thus, the frequency is 12 Hz. In the bottom figure, figure B, we see that there are 6 periods in 1 second, which makes each period equal to 1/6 of a second, and thus the frequency is 6 Hz. Phase is the position of a point in time or an instant on a waveform cycle. A complete cycle is defined as an interval required for the waveform to return to its arbitrary initial value. The graph to the right shows how one cycle constitutes 360 degrees of phase. The graph also shows how phase is sometimes expressed in radians, where 1 radian of phase equals approximately 57.3 degrees. Phase can also be an expression of relative displacement between two corresponding features, for example, peaks or zero crossings of two waveforms having the same frequency. In sinusoidal functions, or in waves, phase has two different but closely related meanings. One is the initial angle of a sinusoidal function at its origin and is sometimes called phase offset or phase difference. Another usage is the fraction of the wave cycle that has elapsed relative to the origin. We can see the phase shift in the left figure by 90 degrees and 180 degrees by where the sine waves begin. We will now take a look at an example of how to calculate the phase in degrees and radians. It is important to notice that the calculation of phase is in radians or relative to pi. Since the problem states that the sine wave is offset by 1/6 of a cycle with respect to time 0, we take 1/6 times 360 because one complete cycle is 360 degrees. This gives us 60 degrees. To get radians, we need to convert from degrees to radians. One complete cycle or period is 360 degrees, which is equivalent to 2 pi radians. Thus, we take the 60 degrees and multiply it by 2 pi over 360 radians to get pi over 3 radians, which is equal to 1.046 radians. The general sine wave can be represented by the mathematical formula as shown at the top of the slide, which is S of t equals a times sine of 2 pi ft plus phi. A represents peak amplitude, f represents frequency, phi represents phase, and t represents time. This is known as a sinusoid function. The figure shows examples of what happens when we change each of the three different parameters. The horizontal x-axis is time in seconds, while the vertical y-axis is the sinusoid function. In the upper left figure, figure A, the frequency is 1 Hz because we see one complete cycle within 1 second of time. The peak amplitude is at 1 and phase is at 0. Substituting those values into the formula for a sine wave, we get S of t equals sine of 2 pi t. In the upper right figure, figure B, we see that amplitude has now changed to be 0.5, but frequency is 1 and phase is still at 0. Substituting those values into the equation for a sine wave, we get S of t equals 0.5 times sine of 2 pi t. In the lower left figure, figure C, we have a peak amplitude of 1, but now a frequency of 2 Hz, because we see two complete cycles within 1 second of time. Phase is still at 0. Substituting those values into the formula for a sine wave, this wave is now S of t equals sine of 4 pi t. Finally, in the lower right figure, figure D, we now see a phase shift of pi over 4 radians, which is 45 degrees. So notice the difference of where the sine wave starts. Frequency is still 1, and amplitude is still 1. Thus, the formula for this wave is now S of t equals sine of 2 pi t plus pi over 4. Generally, the power in your house can be represented by a sine wave with a peak amplitude of 155 to 170 volts, but household voltage is normally stated as being 120 volts. This discrepancy in the values is because this is a root mean square or RMS value. The root mean square is not a statistic you hear too much about because it is mostly used as part of other statistics, such as the standard deviation, which are much more famous. The root mean square is a measure of the magnitude of a set of numbers. The root mean square is computed by squaring the voltage to make everything positive, finding the average, and taking the square root. There is a simple relationship between two sine waves, one in time and one in space. The wavelength, represented by lambda of a signal, is the distance between identical points in the adjacent cycles of a waveform signal. Assume that the signal is traveling with a velocity v, then the wavelength is related to the period as follows. Lambda equals v times t. Remember that period t equals 1 divided by f, so substituting that into the formula and solving for v, we get an equivalent formula of lambda f equals v. In the case where v equals c, which is the speed of light in free space, c is a constant that equals 3 times 10 to the 8th meters per second. The wavelength, lambda, of a wave is the distance from any point on one wave to the same point on the next wave. To avoid confusion, it is best to measure the wavelength from the top of a crest to the top of the next crest, or from the bottom of a trough to the bottom of the next trough. Wavelength is measured in meters, since it is length after all. The frequency f of a wave is the number of waves passing a point in a certain time. We normally use a time of 1 second, so this gives us frequency, the unit hertz, since 1 hertz is equal to 1 wave per second. Don't get confused with this quantity frequency. It is not a distance traveled by waves, nor is it a speed, although it is linked to both of these quantities. For water waves and sound waves, the unit hertz is usually good enough, but radio and TV waves have such a high frequency that the kilohertz or even the megahertz are better units. In practice, an electromagnetic signal will be made up of many frequencies. It can be shown using a discipline known as Fourier analysis that any signal is made up of components at various frequencies, in which each component is a sine wave or sinusoid. By adding together enough sinusoidal signals, each with the appropriate amplitude, frequency, and phase, any electromagnetic signal can be constructed. As mentioned before, a signal is made up of components at various frequencies. Basically, it is a combination of different waveforms. In the figure, we see two different sine waves in figures A and B. Figure A is our traditional sine wave with an amplitude of 1, frequency of 1 Hz, and phase of 0. Figure B is a sine wave with an amplitude of 1/3, frequency of 3 Hz, and a phase of 0. Figures A and B can be combined to create a new sine wave that approximates a square digital wave in which the formula for that wave is shown in the figure C. The components of this signal are just sine waves of frequencies f and 3f, which are included in the formulas for the sine waves from figures A and B. Essentially, the wave in figure C is just the waves from figures A and B added together. For each signal, the time domain function, s of t, specifies the amplitude of the signal at each instant in time. However, there is a frequency domain function, s of f, that specifies the peak amplitude of the constituent frequencies of the signal. The top figure, figure A, shows the frequency domain function for the signal shown in the bottom figure, figure B. Figure B shows the frequency domain function for a single square pulse. The frequency domain function is continuous and has non-zero values indefinitely, although the magnitude of the frequency components rapidly shrinks for larger f. In this example, we see that the sine wave has a frequency of 6 Hz since it has 6 cycles in 1 second. The peak amplitude is 5 volts. This is for the time domain, and notice that the x-axis is time in seconds. In the frequency domain, notice that the x-axis is frequency in Hertz. We can plot this same sine wave as a discrete line at 6, since the sine wave has a frequency of 6 Hz up to the amplitude of 5 volts. In this example, we have 3 different waves: the blue with a frequency of 0 Hz and amplitude of 15 volts, the red with frequency of 8 Hz and amplitude of 10 volts, and the green with frequency of 16 Hz and amplitude of 5 volts. These 3 signals can each be represented in the frequency domain by plotting discrete vertical lines of their frequency and amplitude. The spectrum of a signal is the range of frequencies that it contains. For example, from the previous slide, if we hypothetically treat the 3 waves as one combined signal, the spectrum will extend from 0 to 16. The absolute bandwidth of a signal is the width of the spectrum. For example, from the previous slide, the absolute bandwidth is the difference of the highest frequency and the lowest frequency, which is 16 minus 0, which is equal to 16. Many signals, however, have infinite bandwidth. The effective bandwidth, or just bandwidth, is a narrow band of frequencies containing most of the energy in a signal. If a signal includes a component of 0 frequency, it is a direct current, or DC, or constant component. Although a given waveform may contain frequencies over a very broad range, any transmission system will be able to accommodate only a limited band of frequencies. This, in turn, limits the data rate that can be carried on the transmission medium. A square wave has an infinite number of frequency components, and hence an infinite bandwidth. However, the peak amplitude of the kth frequency component, kf, is only 1 divided by k, so most of the energy in this waveform is in the first few frequency components. In general, any digital waveform will have infinite bandwidth. If we attempt to transmit this waveform as a signal over any medium, the transmission system will limit the bandwidth that can be transmitted. For any given medium, the greater the bandwidth transmitted, the greater the cost. The more limited the bandwidth, the greater the distortion, and the greater the potential for error by the receiver. There is a direct relationship between data rate and bandwidth. The higher the data rate of a signal, the greater is its required effective bandwidth. In both periodic and non-periodic signals, the bandwidth is computed by taking the difference of the highest frequency with the lowest frequency. Thus, in this example, the highest frequency is 5,000 Hz and the lowest frequency is 1,000 Hz. So, the bandwidth is equal to 5,000 minus 1,000, which is equal to 4,000 Hz. Here is another example of computing bandwidth. If a periodic signal is decomposed into 5 sine waves with frequencies of 100, 300, 500, 700, and 900 Hz, what is its bandwidth? To solve this problem, we simply take the highest frequency and subtract by the lowest frequency. So 900 minus 100 will give us 800 Hz. To draw the spectrum, we plot each wave as a discrete vertical line where its frequency lies on the x-axis and an amplitude of 10 volts on the y-axis. So let's take the following example. A non-periodic composite signal has a bandwidth of 200 kHz with a middle frequency of 140 kHz and peak amplitude of 20 volts. The 2 extreme frequencies have an amplitude of 0. Draw the frequency domain of the signal. So we know that we have the high peak of the bandwidth and 2 sides are 0. Since the bandwidth is at 200 kHz and the mid-range of the signal is at 140 kHz, then the signal must start at 40 kHz and end at 240 kHz. It is also important to notice that the peak amplitude of the middle frequency is 20 volts. This is also known as a sawtooth signal. It has a lot of use, especially in submarines. We have already seen that the terms analog and digital roughly correspond to continuous and discrete, respectively. Data is defined as entities that convey meaning or information. Signals are electric or electromagnetic representations of data, whereas signaling is the physical propagation of the signal along a suitable medium. The term transmission means the communication of data by the propagation and processing of signals. As we stated before, analog data takes on continuous values in some interval, the most familiar example being audio, which in the form of acoustic sound waves can be perceived directly by human beings. The figure shows the acoustic spectrum for human speech and for music. Notice that both the x and y axes are in log scales. Frequency components of typical speech may be found between approximately 100 Hz and 7 kHz, and has a dynamic range of about 25 decibels. A shout is approximately 300 times louder than a whisper. Another common example of analog data is video, as seen on a TV screen. The most familiar example of analog information is audio or acoustic sound wave information, for example, human speech. It is easily converted to an electromagnetic signal for transmission. All of the sound frequencies whose amplitude is measured in terms of loudness are converted into electromagnetic frequencies whose amplitude is measured in volts. The telephone handset consists of a simple mechanism for making such a conversion. In the case of voice data, the data can be represented directly by an electromagnetic signal occupying the same spectrum. The spectrum of speech is approximately 100 Hz to 7 kHz, although a much narrower bandwidth will produce acceptable voice reproduction. The standard spectrum for a voice channel is 300 to 3400 Hz. Now consider a video signal produced by a TV camera. The US standard is 525 lines, with 42 lines lost during vertical retrace. Thus, the horizontal scanning frequency is 525 lines times 30 scans, which is equal to 15,750 lines per second, or 63.5 microseconds per line. Of the 63.5 microseconds, about 11 microseconds are allowed for horizontal retrace, leaving a total of 52.5 microseconds per video line. To estimate the bandwidth needed, we use maximum frequency when the lines alternate from black to white. The subjective resolution is about 70% of the 525 lines minus the 42 lines lost during vertical retrace, which is about 338 lines. We want horizontal and vertical resolutions to be about the same, and since the ratio of width to height of a TV screen is 4:3, so the horizontal resolution computes to about 4 divided by 3 times 338, which is equal to 450 lines. As a worst-case scenario, a scanning line could be made up of 450 elements alternating black and white. That is 450 divided by 2, which gives us the 225 cycles of the wave in 52.5 microseconds, for a maximum frequency of about 4.2 megahertz. Therefore, the bandwidth of the video signal is about 4 megahertz.